we are now going to take a look at the definite integral. Here's a little bit about how the definite integral comes together and makes sense. In the end, it's relatively easy to do. These are different ways of approximating the area underneath of a curve. So you may have heard of the trapezoidal rule. In AI, they actually have to talk about the trapezoidal rule, which is just splitting it into trapezoids to approximate it. These are called Riemann sums, and they're made of taking different rectangles to approximate the area under the curve. And you can either do always on the left side of a, here we go, on one of the sides, the left side of a rectangle. These are all a little bit different. On the right side of the rectangle where it meets the curve, or you could do the upper bound or the lower bound here. But as you get more and more rectangles, you're getting closer to the area. So this is the important idea, and you're converging to a certain value. So if you look at this is called the definite integral here. You've already seen it without the boundaries for the indefinite integral. It didn't have defined boundaries. What this is it's saying you're adding up. This big extended S means the sum. This is the sum from the starting to the ending point, just like in the sigma notation for adding things together to the end. This is the height of the rectangles, of each of the rectangles, of course, on the y value, and this is how wide each rectangle is. And as with things in calculus, we're approaching infinity, getting infinitesimally small, so the change in x. So if you multiply the height of the rectangle by the width of the rectangle, you get the area of each rectangle here. So you're adding up all these rectangles that are getting smaller and smaller in width and getting closer and closer to the approximation of your area under the curve. It's actually quite easy to calculate. So you have this notation with your boundaries, and all you have to do, this is the antiderivative, which we've been finding. You find the antiderivative of these, or of the singular function in it, and then you substitute in the upper bound and then take away from the lower bound. Both of those are the antiderivatives. That's a relatively common notation. So here's an example where you have a definite integral from 0 to pi, and you want to find the area under this curve, or it is slightly different of what that is, but that's fine for now. You need to find the antiderivative first, so we're still going to do that. I'm going to show the notation as we go through. The antiderivative is 6 sine of 3x. Remember, we have to negative 6. I'm going to take it slowly here. Cosine, make sure to divide out by the chain. We can check stuff after. Plus, this is going to be 2x squared. So this is the antiderivative.
Yes, she's recording right now.
And then the way you indicate that you still have these boundaries is you do now a straight line from A to B. In this case, sorry, my A is 0 and my B is pi. Those are the boundaries. You don't need to label this, of course, every time. And all you're going to do is substitute now. First, the upper one, and then take away the lower one. And you may notice I don't have C, because when you're looking at a definite integral, what you would get is you have C at the end of this, and then you take away C with your lower bound. So you don't need to do C here. So first, we're going to substitute in the pi into each place. And then you're going to take away when you substitute in 0. Okay, so upper bound and lower bound. Here, I'll put this. And here's the lower bound. 3 pi. So remember that 3 pi, the cosine of 3 pi is going to be negative 1. So we have negative 2 times negative 1 plus 2 pi squared. I'm not going to approximate that. That's absolutely fine to leave like this. Plus cosine of 0, and cosine of 0 is positive 1, times negative 2 is going to be negative 2, and then times a negative again, so plus 2, and that's going to be 0. And if you simplify this, you get 4 plus 2 pi squared. And that you could approximate out. I'm not going to here, and you would find approximately the area under the curve, slightly different depending on how much is above or below, but you don't need to worry about that for now. It is the definite integral at the very least. Here's another example. This one looks a little bit different. We're going to use the u substitution that we used before. Here is the chain of that. So if you're saying, okay, well, to find this antiderivative first in all cases, we're going to say, let this be u, 2x squared plus 3x plus 6. du is then 4x plus 3 dx. And when we substitute this back in, we still have our upper and lower bounds of u du. Oops, excuse me, u du. There are no squareds, there's nothing else happening. And the antiderivative of that is 1/2 u squared. We still need our bounds from 1 to 2. 1 to 2, put those in. We always start with our upper bound, so 1/2 2 squared minus 1/2 of 1 squared. And that's going to be, I think I'm running out of room here, 4/2 of that is 2 minus 1/2, or 1.5. There. Okay, so it's just the antiderivative and then substituting in the bounds. And what you could do is find things like this, so the area bound by curves. Find the area bound by the function f of x equals 9 minus x squared and the x and y axis. So you may need to remember what these look like. Okay, maybe you can use a calculator if it's a paper 2 or 3 question. This is just a regular parabola that has been reflected across the x-axis, so vertically and up 9. So it still has this line of symmetry. And of course, then it's going to cross the bound. Here's 3. And that's important because we don't actually know our upper and lower bounds unless we know what this looks like. Our boundaries are always x values. So this area is what they're looking for. We want to find from 0 to 3 from our function dx. Find the antiderivative of it, 9x minus 1/3 x cubed from 3 to 0. 9 times 3 minus 1/3, 3 cubed. Of course, this is going to be 0 when you take away the lower bound, but I'll be somewhat pedantic about it here. Hopefully you can still see that, okay? And you're going to get 27 minus 9 minus 0. So 18. This would be the area under this curve. Units, we don't have any other units here, so units squared. Okay, what's really nice is you can do these quite simply on the calculator. I'm just going to show it on here. Turn it on, and just like the way we found derivatives, the notation on this is pretty good. Let me delete all of this so it's not so messy. If you go into math, you will find that you have this definite integral option. It won't be able to find the antiderivative, so we're going to put in 9 minus x squared, but it can tell us the value and do all the work for us for that. So from 0 to 3, again, if you didn't know how to find that, you might want to look at the graph of it in order to find those bounds, and you'll see that the definite integral of 9 minus x squared from 0 to 3 is 18. Here's an example of one that you can't do on your calculator in this way, though. There are different ways with graphing to kind of figure it out, but it's relatively easy to do finding this just by hand. So we're going to go about it the same way. We know that this is equal to the antiderivative from 0 to a, and we want that to equal 0. So when we set up this equation here still, we're going to get 1/4 a to the 4th minus 8a. Okay, well, we don't need that, but I will. Minus, when we put in 0, it's relatively easy to see, but I will anyway, equals 0. So 1/4 a to the 4th minus 8a minus 0. And if you were to simplify this, we could get that a equals 0, but that doesn't make sense. Of course, that makes sense if you don't have any width of a rectangle, then the area of it is 0, so that's kind of a ridiculous statement. But you could use your calculator to solve this. 1/4, it's actually even simpler than that though, minus 8a equals 0. Oops, I forgot the a to the 4th. A cubed, I'm dividing everything by a. We've already taken out that extraneous solution here, that means nothing. Equals 8. I just moved it over, I divided by a as well. It's a little difficult to see here. Multiply by 4 to make that an easier easier number to see, and 8 times 4 is 32. So A is equal to the cube root of 32. Okay, oops, there you go. And that will be the solution to this, to make it equal 0. And why does that equal 0? I said we'd get there because it's not quite the area of the curve yet. So if you were to look at this function, I'm just going to pull it up when I find my calculator. Put it to the side, under stuff. If you look at what this function is, I'm going to delete all of these. X cubed minus 8. Whoops. I need the standard window here. Window, we'll do the standard one. Okay. Now, the square root of 32 is approximately, we'll look here, excuse me, the cube root is what we want. 3.17. So, if you were, again, to look at this graph, and I'm just going to change the window. From 0, it says, and how would I change that? Actually, we can put it in just like that. Do the cube root, probably better to do to the 1 divided by 3. What this is it is going to calculate all of this as negative, and this above the x is positive, and that's saying that these pieces are equal. So this area is equal to this area here. You may have to zoom out a little bit. It may be a little bit hard to see because, of course, that goes up where it crosses here. It will keep going a little bit. I might change this window so that's, maybe that will be in. That will end up being the same. Okay. It's not the whole area. You would have to find out where it crosses the x-axis and split them into parts if you wanted to know the area. We'll do that in another day, though. And then the last one. What is the value of m greater than 0, just to distinguish what it is? If from m to m squared of 1 over x dx equals 1, and the same idea here, find the antiderivative of it, and the antiderivative of 1 over x is ln of x. From m to m squared, we want that to equal 1. So ln of m squared minus ln of m. We're going to need some log laws to make this make sense. Remember that these will come together as division. Ln of m. So this would have to be e. It says it's greater than, of course, we could have had a negative here, but it does say. So, oops. So so m equals e.